Friday, January 31st, 2025. It is my great pleasure to introduce to you Dr. Paul Newton as our CCDC speaker today. Dr. Newton received his bachelor cum laude in applied mathematics and physics at Harvard. Then he got his PhD from applied mathematics at Brown. And then after that, he worked as a postdoc at Stanford University. And then from Stanford, he moved to the University of Champaign, where he was associated with the mathematics department and the Beckman Institute. He was there first as an assistant, then associate. And then since 1993, we welcomed him back into the sunny state of California. He joined USC. He's currently professor of applied mathematics, engineering, quantitative and computational biology, as well as medicine, with a whole host of schools and centers and so forth. He's also a founding affiliate member of the Allison Medical Institute. You can see that proudly displayed.
It's because of temperature only.
It's a temperature-related. And he finds time also to serve as editor-in-chief for the Journal of Nonlinear Science. It's a Springer Nature journal. It's a for-profit journal, so we'll ask him about all the income that he makes from that engagement. And finally, he recently elected a fellow of the AAAS, Guggenheim Fellow for his work on mathematical methods to handle tumor subpopulations. So in fact, that's the subject of today's talk. Paul, it's a great pleasure to have you. Welcome.
Thank you very much. I really appreciate the invitation. I love coming here. This is my favorite group because lots of friends, but also we have lots of scientific things in common, but maybe with slightly different techniques and applications. So it's always fun visiting. So I'm going to talk about the control of evolutionary mean field games, and the last part of the talk, maybe 20 minutes, I'll talk about applications in tumor cell population models, which I've been working on for quite a while. The two grad students right now that are working on these topics are Tina Stuckey, who actually was an undergrad here. I think she told me, I think she was in applied math and physics, a double major. And then Matt, who's kind of in the middle of his PhD journey. Tina's more on the end of it. So a lot of what I'm talking about, Tina had a hand in. And then I've had various students working on these models, which are basically the replicator dynamics models, which are a really, really cool nonlinear system that have lots of applications in many, many fields. And so I'll introduce you to those and then get into some applications. So here we go. And interrupt if you have questions. So let me start out. I'll start out by giving a little introduction to some of the applications that we've been working on through this MURI that we have on microbial population dynamics and some of the general themes that my group is focused on. I'll give you a little introduction into the replicator dynamical system and what those are about. And then the first problem I'll tell you about is kind of in some ways a baby startup problem, but it's a good vehicle to show you the aspects of the replicator equations that are useful and interesting, and also how it combines with control theory. Problem two is the main thing that I've been working on for quite a while, that has to do with optimizing chemotherapy and immunotherapy schedules in order to steer the evolution of a tumor, of the subpopulations that make up a tumor. And then hopefully I'll have time. I'll give one slide because I know everybody's going to ask me this question, so I'm going to head it off, and that is I'm going to show how we would use these models for patient data, and then end with an ongoing project that we're working on. All right, so let me start out with what mean field dynamical systems are in general. And these are dynamical systems where the individual players obtain their update rules from properties of the mean field. Okay, so that's sort of a broad statement. So we've worked on these kinds of models in various settings, and I'm going to peel off a couple of these and go into more detail, but let me just give you kind of a overview quickly. The first one is an ant beetle population model I work on with Joe Parker at Caltech. The situation there is you have these large ant populations, very aggressive ants, and then you have small numbers of beetles who have learned these techniques, chemical masking techniques, in order that they sort of are embraced as one of the ants. And so they can survive and live and feed off of the ants without being recognized as being kind of predators. Another one is microbial populations, which I work on with various people under the umbrella of this MURI that we have. James Bodeker is the main guy in physics at USC. And this is basically co-evolutionary dynamics of microbial populations. Very, very similar kinds of models as tumor cell populations and very similar kinds of techniques. Instead of chemotherapy, you're doing antibiotic treatments, time-dependent. And so there's some nice models there. And then tumor cell population models, which, as I said, I spend most of my time on, and mostly with a group at the Moffitt Cancer Center, where I have an ex-PhD student who's a faculty member there now in a really cool department called the Integrative Mathematical Oncology Department. And they're embedded within a big cancer center, and so they're actually running clinical trials using adaptive control theory in small settings on very specific targeted populations. So it's fun. I will tell you a little bit about, so the problem one, which was the startup problem that I'm going to tell you about, is COVID-19 vaccine uptake as a reinforcement learning dynamic. And we think of then as how you would control, give rewards and punishments in order to increase the percentage of people that choose to get vaccinated. Mean field games have been around for a while. Actually, probably the most well-known one would be the synchronized oscillator problem, where you have metronomes and they're sitting on a table like this and they're all independently oscillating. But as soon as you put them on a platform that is able to roll right and left based on the average motion of the population of metronomes, they start to synchronize. Awesome problem. I know he's worked on it a little bit, and I've never really worked on it, but it's definitely a guiding light in a lot of what I do. I think Jeff works on problems like this and so forth. My favorite problem, which I didn't realize was a mean field, it's not really a dynamical system, but we've been using this for 25 years. It's a kind of a hobby of mine to build models for forecasting tennis outcomes. And it's actually a mean field. Our approach is a mean field approach because it's very difficult to forecast head-to-head competition between two players, any two players, because there's not that many head-to-head matchups. Even matchups between two illustrious players like these two characters, there's really not that many over a one-year period. And so it's really not very stable to do forecasting models based on that. So instead, what we do is we look at the whole field of players over years, hundreds of players, and we take averages of the parameters, the field variables, and then we base our model on the individual parameters of each player as compared with the field. And so basically we're adopting kind of a mean field approach for that. All right, so let me now get into a little bit more detail, maybe a little history. So agent-based models and evolutionary games are related. They're not identical, but they are related. So I know many of you are familiar with agent-based models. Illustrious history, Ulam, Conway, Holland used them. So with agent-based models, it's an explicit modeling approach if you know the pairwise interaction laws between the players. All right? And it typically includes spatial structure, so people like that. The problem is with agent-based models is they're challenging for a large number of agents because then you have interaction pairs with large numbers of agents. It gets harder and harder as the number of agents increases. It's not typically used in studies where evolution by natural selection is important. On the other hand, mean field evolutionary games, as I say, are somewhat related in spirit in that you're modeling populations of agents, but they're very different. So John Maynard Smith is probably the person most responsible for developing evolutionary game theory in the biological context because it's ideal for understanding survival of the fittest, natural selection, and so forth. I think the first people that actually wrote down the replicator equations are Taylor and Yonker in the late 70s in a very crude form, but basically the ingredients were there. And then probably Martin Nowak at Harvard is maybe the person most, in some ways, most known for developing the field. But there's also another group of people, including Pierre-Louis Lyons and René Carmona and Mette Soner and Sean Mine, people like that, who have been developing mean field games from a little bit of a different point of view. It's not exactly the same kind of thing that I'm going to talk about today, but it is related. All right. These models are based on the relative fitness of each of the subpopulations that are competing versus the mean field. Okay? So the thing about comparing your behavior with respect to a mean field is that basically your models improve the larger the population is, because the mean field gets more and more stable. So it has the opposite kind of attractiveness as agent-based. It improves with larger population sizes. And these kinds of models are ideal for studying evolution by natural selection because successful strategies get mimicked more often than not. And so successful strategies, and I'll tell you more about that as we go, emerge from the dynamics because of imitation or heredity. The basic equations that I'll talk about are the replicator dynamics and the related adjusted replicator dynamics. All right. Questions, comments? All right. Thumbs up from Francesco. Okay, I'll keep going. Okay, so I'm going to peel off these three examples and talk much more about those two. But let me just start here to give you a sense of the unity of these models. So n sub I, little n, is a number of agents in subpopulation I. And these subpopulations are competing against each other. So in principle, you can have as many competing subpopulations as you want. Capital N is the total number of agents. So you're summing over I. And the state variables, xi, are little n sub I over the total number. So it's a fraction, or it's a percentage between 0 and 1, a frequency. So the state variable is a frequency in the population, always normalized between 0 and 1. And the sum of all these frequencies is 1. Okay? So that's the setup, starting setup. And so in different problems, you can have controllers that you interpret in different ways. So the controllers in these problems act on the subpopulation x sub I. All right? So for example, in the ant beetle problem, the controller we think of as the beetle's chemical action that they perform in order to increase their survival in this population of hostile agents. All right? In the COVID-19 problem, which I will talk about, the controllers are the vaccine incentives that you might give or punishments that you might give in order to get people to vaccinate. So the percentage of the population that's vaccinated is going to be a Nash equilibrium of the evolutionary game, and the dynamics will flow towards that Nash equilibrium. And what you do is we do optimal control in order to optimize the incentive programs in order to increase that Nash equilibrium. In the last problem, which occupies basically all of my time, is the co-evolutionary dynamics of tumor cell populations. And for that problem, the controllers will be the chemotoxins or the immunotherapies, and how you time them and how you combine them. And so just to get you used to the variables here, so let's just say you have a cartoon tumor which has 3 different phenotypes of cancer cells. You have sensitive cells that are cancer cells that are sensitive to the 2 different, let's just say you have 2 different chemotoxins, and the sensitive cells are killed by both of those chemotoxins. And then you have resistant populations that have undergone mutations in order to make them resistant to certain chemicals. And so let's just say you have resistant population number 1 that's resistant to chemical number 1, and you have resistant population 2 that's resistant to chemo number 2. And so you use combinations of those drugs, drug cocktails, and you use timing in order to steer the dynamics of that tumor to get it to a beneficial state. A lot more about that later. All right. So it's also really important to understand the number of agents that you're talking about from a stochastic versus a deterministic point of view. So in the beetle ant problem, which is the smallest individual problem that we're talking about, you're looking at 5 or so beetles in a population of 100 or a couple of hundred ants. Those numbers are very small in general. And so in a problem, and there's 2 populations, and they sum to 1, all right? On the other hand, in the COVID vaccine problem, that's, let's say, the population of the United States, or whatever population you're looking at, but let's say the United States, these are vaccine adopters, vaccine hesitant. That's a large population, still 2 populations, 2 subpopulations, but the numbers are large. And in a tumor problem, that's more complicated because, so let's just say in a medium developed tumor, you have 10 to the 3 to 10 to the 5 chemosensitive cells, and then you have a couple of maybe 10 to 100 resistant cells, different kinds of mutations, and they're just kind of residing in that tumor. And meanwhile, you're all concerned with the chemosensitive cells because that's what's driving the growth of the tumor. And then when you get rid of those, all of a sudden, these resistant cells have no competition and they bloom, and that's called competitive release. So, but it does depend a lot on what stage you recognize the tumor. So if you're interested in early stage tumors, which we are, then the numbers are much smaller than this. And the reason I'm focused on this is because of this. These models are stochastic when there's a finite number of cells, and they're deterministic in the limit as n goes to infinity. And the deterministic equations are the expectation values associated with the stochastic problem. This is a Markov process. This is a nonlinear dynamics problem. And the fluctuations in the stochastic problem go to 0 like 1 over square root of n. So in a problem like this, the stochastic fluctuations will be super important. And in a problem like this, not so important. But in the tumor cell problem, definitely interesting, definitely important. All right. Incidentally, there's a really nice paper by Arne Trauson, who's a physicist, in Germany, has a Max Planck Institute group, co-evolutionary dynamics from finite to infinite populations. Fantastic paper, sort of laying out a lot of the details of this, of these equations. All right. Questions? All right. So let me show you a little bit more about these equations. So let's just take a simple case. So in the beetle ant problem, all right, this turns out to be a hawk-dove problem, which might not mean anything to you, but basically it's a dynamical system with a coexistent state that is asymptotically stable. And so the dynamics associated with these equations, which I'll tell you about in a minute, leads to an internal asymptotically stable equilibrium point, which is called an evolutionary stable trajectory in the context of an evolutionary game. The thing is, in a stochastic version of this, where there's not many, then you want to avoid the endpoints because you don't want stochastic fluctuations to knock you out of the game. All right, the beetles definitely don't want to just have a bad day and die and none left. Okay, so that's one reason why stochastic fluctuations are so important for small populations. And it turns out, Tina has worked out the in this model. So here's, let me show you this first. So in the hawk-dove beetle ant problem, the dynamics in blue, the deterministic dynamics, takes you to this internal asymptotically stable point. But the finite population model, as I said, is a Markov process, and that's stochastic. And so fluctuations, particularly when your internal equilibrium point is small, have the possibility of knocking you out, all right? And so it's a combination of where the internal fixed point is and the size of the fluctuations and so forth. So this formula, which is nice, gives you the mean extinction time as a function of n. So she worked out, for two populations, she worked out this formula and then did the asymptotic expansion for large n. And so what that shows, this is log of the expectation time divided by n. So you multiply that by n, you take the exponent. So as n goes to infinity, the mean extinction time goes to infinity because the fluctuations go to 0. All right, but it goes exactly at that rate. So the question is, in this context, can the beetles avoid extinction, reduce their risk of being killed by the swarm using active survival techniques like chemical defense gland use, chemical invisibility, and cloaking, is what Joe Parker, the words he uses, and I channel those words to you. Yeah. In the 3-population tumor problem, so now the sensitive cells, resistant cells 1, resistant cells 2, is more complicated just because it's more subpopulations, but of course you can imagine even more than that. But you want to avoid hitting any of the boundaries of this discrete triangle. It's a triangle because of the sum to 1, and so we've just chosen a value of n just to make it a nice picture. So the selection dynamics, so there's a finite n stochastic Markov process, and this is a picture of the selection dynamics in a tumor. And the thing is, so in that problem, in order to avoid extinction, you basically want to go to, let's say, the midpoint of that triangle, where there's a balance of the coexistence of these subpopulations, S, R1, and R2. And so you need some measure of that. And so the way we do that is we use something called the Shannon diversity of these populations, which is a simple thing, obviously. It just basically takes you to a point where each of the populations is 1/3. That's the maximum diversity, which is that point in red. And so then you can draw the contour plots associated with that. And so you can ask yourself, if you have a tumor that has a general makeup of these 3 populations, what kind of chemotherapy schedule would you use in order to get you to that point? All right. Well, the gold standard would be, why don't I just do gradient climbing up that entropy landscape? Sure, absolutely. Go there and go to that red point. The question is, how are you going to do that? What is your control chemotherapy schedule that mimics climbing up an entropy landscape? Complicated question. So, question 2, can we compute optimal chemotherapy schedules that maintain diversity and avoid extinction? Okay. And another little thing is that even if you're successful at getting to that red point, that's not a fixed point of the system in any sense of the word. So even if you get there, you have to figure out some chemotherapy schedule to keep you there. So, yeah.
Why would you want to eliminate the resistance?
Excellent. Well, okay, almost an excellent question, except that last little part. So I thought you were going to ask, why wouldn't you want to eliminate the sensitive cells? Because those are the bulk of the tumor, and that's true. But the problem is that one of the main problems with chemotherapy is that you get chemo-resistance. And one of the ways you get chemo-resistance is you eliminate the sensitive population, which is suppressing the resistance cells, and then all of a sudden the resistance cells have free reign, and they grow, and then you're screwed because your chemo doesn't work.
Yeah, right. So why don't you want to eliminate the resistance cells? But of course, that you can want to.
Yes. Perfect. Yeah, Jeff.
I had basically the same question. Yeah, it's not obvious to me that that's the best target.
No, it isn't obvious. That's true. So it's a combination of trying to avoid chemo-resistance while also shrinking the volume of the tumor. It's those combination of things. So typically in these problems, you have replicator dynamics, and then you have a tack-on equation, which is a volume equation, which is the volume of the tumor, which you don't get from replicator because that's all fractional. All right. So everything I've said, I would pack in a single little phrase, and that is, can we shape the transient dynamics associated with these interacting subpopulations? All right, so the general theme of most of what I do is use control theory on mean field evolutionary games to avoid stochastic extinction, to maintain Shannon diversity, and to shape the transient dynamics in beneficial ways. So I'll walk you through examples of these things. All right, any other? Igor, got a question? You look like you're ready.
So,
I know, I could tell.
if you are at a Nash equilibrium, and you have stochastics in the picture,
Yeah.
does linear response theory come into play?
Probably, but I mean, I haven't looked at it from that point of view because we have the full nonlinear equations, and so basically we're trying to control the full nonlinear equations. But it is possible that you could linearize if you, maybe we could talk about it at the end. But basically in problems like this, you don't necessarily even know what the Nash equilibria are. You basically are going to run the replicator dynamics, which I'll show you, in order to find the Nash equilibria. And so, yes, I mean, in principle, I think your thought process.
There is a Royal extension of the classical linear response theory for arbitrary states that actually does capture.
Okay. Yeah, it could be. I haven't really thought about it in that point of view, yeah.
So could you back up on the slide?
I think I can.
No, maybe keep back.
Oh, more?
I'll tell you later.
I'm not sure I can do that.
There we go. Okay, so the upper left, this reminds me of stochastic chemical kinetics. And the question that comes to mind when I thought is, do all trajectories with finite initial conditions go to extinction with probability 1 eventually? If we wait long enough, is that the only sink in this problem? Is that where they have to go?
It's certainly absorbing states. I don't think so. I think that a certain percentage is going to go to the fixed point. So I don't think so.
So I want to show you when we talk.
Okay.
That was the other version of that problem.
Okay, good. That's another reason why I like coming here. I like the talk at the beginning so that we can split off during the day. I've never been to a university where the talk is at the beginning of the visit. It's almost always at the end. And by then it's like too late. Okay, so replicator dynamics. So the simplest is two populations, and so let me walk you through that and then not go into details so much on the three population. So two competing subpopulations, we're calling them X1 and X2. They sum to 1, so Xi measures the fraction of the population in this two population model. You have to have a payoff matrix associated with these problems, and in this case it will be a 2x2 payoff matrix, and that defines the evolutionary game being played. And A, B, C, D are interaction coefficients that give you the fitness when the two different populations interact, or when when X1 interacts with X1, and so forth. All right. So the state variable is the vector X, 1, X2, and I'm showing you the deterministic case, n equal infinity. And so these are the replicator dynamical system. This is the replicator dynamical system. It's a coupled system, in this case, of two nonlinear ODEs, which I'll peel out in a minute. You have the payoff matrix here, and it turns out to be cubic equations, as you probably can see. So I like writing it this way. You divide each by that. So these are the logarithmic growth rates of each of the populations. And the right-hand sides then are the update rules on the growth rates. And so these terms are the fitness of each subpopulation, 1 and 2. This is the first component of this vector. This is the second component of this vector. And these are the average fitness. And so you're comparing the fitness of each of the subpopulations with the average. And another phrase that I will explain in a second, this is an important aspect of this, is there's frequency-dependent selection, because the selection mechanism on the right depends on X. And so it's frequency dependent. And that's an important part of all of these problems. And and that's the growth rate of each subpopulation. So if there are more subpopulations, then you have larger and larger systems, but basically the structure of these equations is all the same. Okay, so the beetle-ant system turns out to be a hawk-dove problem, an anti-coordination game. The Nash equilibrium is opposite strategies. The ants are the hawks, the beetles are the doves. And the tumor dynamics, or microbial population problem, turns out to be a prisoner's dilemma game, where the cancer cells are the defectors, they have higher fitness. The healthy cells are the cooperators, they have lower fitness. That's why the cancer cells take over the population if there's no control. And the Nash equilibrium without control theory is that everybody defects, meaning the cancer population takes over, and you have a lower average fitness. Okay, so the standard prisoner's dilemma matrix in a two-component problem, the lower row dominates the upper row. You have cooperators and defectors, and the Nash equilibrium is the all defect state. And so that matrix is embedded in those equations. And so the nice thing about these problems is there's no rationality assumed in the replicator dynamics. Basically, the Nash equilibrium emerges from the nonlinear dynamics of that problem. The finite cell problem, I'm not going to go into all the details, but I'm just going to show you that it's a Markov process, and the transition probabilities, it's like a Moran process, if that means anything to you. It's a birth-death process where the birth and death rates are weighted according to the fitnesses of the subpopulations. The important thing is that that for the finite cell model, you have to divide the right-hand side by the average fitness, because you can think of this as the fluctuations of the fitness of each of the subpopulations around the mean, and you have to normalize that somehow, and you normalize that by the average. And so this is the equation that in the limit as n goes to infinity approaches this, but with a divided by the average. All right, so we introduce control into the payoff matrix. So let me just call it C1 of t and C2 of t. It doesn't matter so much whether you do it on the diagonal terms or the off-diagonal terms. We tend to do it on the off-diagonal terms. I'll show you why in the next slide. Okay, in the two-population model, you can uncouple the equations because x1 plus x2 equals 1. It's useful to do that just to understand what's going on. So that's the cubic equation for x1. That's the cubic equation for x2. A, B, C, D obviously are coefficients. And for that payoff matrix, the Nash equilibrium is the coexistence state, plus you have the transient dynamics that takes you there. And for the tumor cell problem, or let's say for a prisoner's dilemma problem, the defect is the asymptotically stable state, and then you have transient dynamics that takes you there. So let me highlight the following, that if you make, so now I'm putting the controllers in the off-diagonal terms. This is a key point here with respect to control theory. So if you put controllers in the off-diagonal terms, time-dependent controllers, your nonlinear equation looks like this, okay? So those time-dependent coefficients, which are C and B in this case, become time-dependent here, all right? So we're not just controlling the linear term here. We're controlling all the coefficients of this cubic equation. And that's what I mean by shaping the dynamics, okay? So you only have two controllers, but you're trying to shape all the coefficients in order to achieve something, all right? So the reason we put it in the off-diagonal terms is purely stylistic, and that's because then B shows up as the linear growth term in the x1 equation. And when C1 is positive, then B becomes bigger. So that's useful for us. Whereas for the x2 equation, C is the linear growth term of the x2. And so it's useful for us to think of C2, when it increases, it's increasing the linear growth rate. But I'm telling you, it's not just about linear growth rates. It's about all the coefficients. All right. Okay, so key features of the replicator dynamical system in general. No assumptions are being made on the rationality of the players, unlike classical game theory. Nash equilibria emerge from the dynamics. Successful strategies arise from replication and imitation or heritable mutations, which is why they're models for survival of the fittest. The populations are adapting. They're not optimizing. And fitness is frequency dependent. All right, so these are some of the names, early names of the replicator equations. And this is a particularly nice review article for people like you guys. I'm sure you know this review article. The role of population games and evolutionary dynamics in distributed control systems. Really nice article. I mean, at least I learned a lot from it. Okay, so let me just mention what I mean by frequency dependent, just so it's clear why it's so important in biological problems. So imagine swimmers. Let's say you have a low frequency population of swimmers, and then you have a high frequency population of swimmers. And then all of a sudden, one of the swimmers has a mutation and develops a tail, which gives it higher fitness, and because it can swim faster and get to its target faster. But that same mutation in a crowded population gives no fitness advantage whatsoever. Okay, so that same mutation, it depends on how crowded the population. That's frequency dependent fitness. It doesn't
assume that they're all competing for limited resources.
Yes, let's just say they're all going after. Let's say these are sperm cells, and they're all going after a egg. Okay, so fitness is frequency dependent, and in our problem, as I said, this is our fitness. And in similar models, but different, for example, local Volterra models, in general, those aren't frequency dependent models. In local Volterra models, there's just a coefficient, which is your linear growth rate. You have interactions, and so you can change those coefficients, but the fitness in a local Volterra model isn't really interpreted this way. All right, problem number 1. Vaccine incentive scheduling using optimal control and the replicator dynamics. So Tina and I developed this problem, and I'll tell you briefly about it. Problem number 2 is our tumor cell population model. All right, so vaccine incentive scheduling. Okay, so here's the basic problem. We got from the CDC data of, let's say, the U.S. population, and also broken down state by state, of the percent of people that were vaccinated during the COVID outbreak as a function of the days since the vaccine was introduced. And so, as you might imagine, it's a curve that looks like that, and then plateaus at some value, which in the U.S. population was around 58%. And so the red curve is something called the Gompertzian curve. The blue is the replicator dynamics, and the dots are the vaccine data. And this is our, just to remind you of the hawk-dove model. All right, so this is the key thing. That's the percent vaccinated in the population. And another key thing is the inflection point associated with that curve, because that's going to set our time scale for doing this modeling. That's capital T. So here are the steps in doing this kind of a model. First of all, we take the data and we fit the uptake data to a 3-parameter Gompertzian curve. So we've got 3 parameters, A, B, and C, and the curve is the one that I show there in red. Step 2 is to use 3 of the variables, f prime at 0, t, and f prime at t, to compute the elements of a 2x2 payoff matrix in the replicator dynamical system. All right. So now we've now computed our replicator equations with that payoff matrix, where our 2 populations are vaccinated and unvaccinated. And so now we understand the transient dynamics associated with the evolution towards this Nash equilibrium. And it turns out, this wasn't a priori given, but it turns out once you do that fitting, it is a hawk-dove evolutionary game with an internal fixed point. And then step 3 is to do optimal control on those entries in order to try to push up that Nash equilibrium. Okay? That's the procedure. All right, so a word about the two populations. Why is the replicator dynamics game relevant in this situation? So let's imagine these two populations, unvaccinated and vaccinated, summing to 1. So I want to back off this thing about vaccinated, unvaccinated. I still want to think of those two groups in that way, but I want to characterize the unvaccinated into a collection of people. One group of people could be eagerly awaiting their turn to be vaccinated, but they're still unvaccinated. Another group could be hesitant but willing in principle. Another group could be skeptical but convincible. And another group could be totally unwilling. Bottom line is they're all basically in this group. And then their vaccinated group is also, could be healthcare workers, they're right away. Could be elderly and immunocompromised right away, early adopters. Maybe there's a group of wait and see people who are trying to look at their neighbors and see if they died and make a decision based on that. But eventually they're going to get vaccinated. And maybe there's people that are waiting for rewards. Show me the money people. They want to wait until they get free plane tickets or whatever. And then there's another group of people that say, force me, and then I'll do it. So obviously there's different kinds of people in each group. And the reason I say that is because the group dynamics influences that thought process. So imagine the following, and this is why the replicator dynamics is so relevant here. So imagine an unvaccinated person in a population of unvaccinated people. They're more likely to think, well, why should I? No one around me is vaccinated. On the other hand, suppose an unvaccinated person is surrounded by a population of vaccinated people. They might say, it seems to be okay. These people are surviving. Maybe it even works. Okay, so their behavior is influenced by the population of people around them. All right. Okay, so control theory. So we use an optimal, we use a cost function, which is a running cost and a terminal cost. And the rewards could be of two types. So there are rewards associated with convincing people to get vaccinated. Could be lotteries, could be gift cards. All of those things were used in different states. And there's also punishments. Lots of different things were used. Can't go to a restaurant, can't get on a plane, things like that. So.
Quick question about the assumption. So it's clearly a fair thing to say I'm influenced by neighbors.
Yeah.
But I've seen the opposite.
Yeah. Yeah.
Which is all these people are crazy and I'm going to get vaccinated. Or all these people are crazy and I'm going
Right.
to say I'm vaccinated.
Right.
Do you adjust for that at all?
I mean, not really, not in our model. We basically.
It's not a big contribution.
I don't know. We didn't get much into social dynamics on this. We just basically had our model and we were doing control theory and we fit data and so forth. So it is a big question of, lots of other questions about rewards and punishment, what works best. We didn't get into that at all. All right, so in this problem I'm going to show you, we're not including a running cost, we're just including a terminal cost, which is basically we want to try to increase the value of the Nash equilibrium. So here's what we do. So as I said, 58% is the uncontrolled population. We are optimizing over a window of time t, which is the inflection point, over n, where n could be some integer. We take 4. But anyway, so in this case, we're optimizing over a window of 22, I think, days. And we are interested in lots of questions. But here would be the controlled problem where we're trying to push 58 up to as high as we can, relative with some constraints on how big a reward we can give. So we can get it up to 71%. And we're also doing the minimization problem, since why not? Okay, so all right, so let me so I'm just showing you now this little window here where we start right near the inflection point, because that's a good place to start, because basically you're watching the pandemic unfold and you're collecting data up to this point, and when you get to that point you have all you need. You have f at 0, you have f prime at t, and you have f of t. Fine, I can now cook up my model and I can go forward with control theory. Okay, so here's an example of the control schedule that achieves this result. So these are the controllers, C1 and C2, off, on and off, and then on and off. And that, the uncontrolled problem would be here, goes up to 29% in this little window. And the control problem knocks it up to here, and that's the result of the optimization. So let me peel that out a little bit, because it's kind of interesting. So this would be a typical result. What time is it, by the way? Oh my gosh. We started late. It is totally your fault. So there's 4 legs of this problem just by the result of when you turn the schedules off and on. What's interesting, so as I said, you shape the dynamics. And so the nonlinear dynamics basically puts you into 4 different games that are switched at just the right times. So it starts out as a prisoner's dilemma. It starts going in that direction for a certain amount of time. Then you go to the next phase, which is the second leg, and it switches, and then it switches, and then it switches, and that gets you to your optimized state. So leg 1, in a sense, is the most interesting and counterintuitive because it goes down for the first part. That's because, I mean, basically it's frequency dependent, and because the controller hasn't really kicked in enough to influence the system much. But once it does, then it starts going up and up and up and gets to that point. All right, not too much about that. We are definitely running out of time. So let me actually, I think you get the point of this model. I want to go to the tumor problem. All right, so here the goal is to delay chemo-resistance in a tumor. So this is what a typical tumor growth curve looks like. That's data from 1964, famous paper by Laird, where they normalized a bunch of data from rats and mice and people and all kinds of things, and they put it all on one graph, and then they fit it to a curve which was Gompertzian, and that is the sort of the standard model that people think of when they think of tumor growth. So think of it this way: you have a first mutated cell, and then you have a tumor carrying capacity. And so we have a stochastic model that does a nice job of creating curves like this. And what's nice about the Gompertzian curve is it naturally kind of breaks down the time dynamics into 4 different regions, inflection point and then inflection points of the inflection point. So you have 4 different regions here. You can think of the first region as being subclinical. It's too early. The tumors aren't even noticed yet. The cells, there are not enough cancer cells. The clinical range is more or less around the red point, and so a lot of people say, oh, tumors grow linearly. Because of course, if you just look around that red dot, it's going to basically be linear. It just depends on where you look. So there's the first driver mutation. Possible dissemination to metastasis, almost certainly for many cancers, occurs way before the tumor is noticed. This would be what people call early diagnosis, which is a reason why there's 10 billion articles on linear growth of tumors, which because they're just looking in that range. And then you start flattening out. Okay, so it is true that it's the linear growth phase where clinical observations typically are made. All right. So here is an important slide that leads me to the replicator dynamics. All right. So imagine what happens in early stage tumor development. You've got a bunch of normal cells, which are these light purple cells, and all of a sudden you have the first clonal mutation, which is what people call the founder cell. And then that starts to grow, and so now you have more and more tumor cells of one particular type, let's say, the red ones. And then all of a sudden, one of those has a mutation, and you have what's called a subclonal mutation, and so now you have a purple cell, and they start to grow. And so now you have a population of 3 different phenotypes, all right? And so let's say you look at the tumor at that time, and you have these 3 competing subtypes. So after a certain amount of time, the tumor is heterogeneous, meaning the subpopulations have different proliferation rates because they have different mutation histories, and they respond differently to different chemotoxins. It's decentralized. There's no queen bee. They're basically all agents. It's stochastic. Fluctuations can be important, particularly in the early stages. And it's distributed because their spatial structure and anatomical locations important, and the spatial locations in the tumor are important. But imagine now you take these 3 subpopulations and you create your model. So now these mutations are pre-existing, all right? And so now in the time period in which you're doing your chemotherapy, you can, let's say, for all practical purposes, ignore mutations, because the chemotherapy timescale is typically very short compared to the timescale in which the thing is developed. Now, I'm not saying that it's not interesting to have mutations that take place during chemo, but that's not what we're considering. All right, so the challenge in standard chemotherapy is that standard chemotherapy, which is open loop control, selects for resistant populations, right? No matter how you do it. You're going to kill the sensitive cells, and that's going to release the resistant cells. Let me not harp on that. So open loop control would be maximum tolerated dose. The chemotherapy schedules they're pre-scheduled, and there's no monitoring of the population. And so that basically kills off the sensitive cell population in red and leaves the resistant population. That's the essence of the problem. And so a better approach is to do closed loop control, where you're actively monitoring the populations, and you're making decisions on when to apply treatment, always leaving some of the sensitive cells in there because they're suppressing the growth of the resistant cells. So those are the clinical trials that are going on at Moffitt. All right, let's see. We are definitely running out of time. So let me show you. So we generally work on the stochastic version of this. So 3 populations, the prisoner's dilemma payoff matrices within each pair of subpopulations. And then we have a tumor growth law that's tacked onto those replicator dynamics equations, which says that the tumor grows with the average fitness of the entire population minus some constant, which is due to the microenvironment. So that system is the typical system we look at. The chemotherapy control parameters are built into how we shape the fitness parameters. Okay, so we have C1 and C2 in this kind of a problem, and we vary C1 and C2 time dependently. And that allows us, in that top equation, to go from the limit of what's called weak selection, where, let's say, Wi is 0, in which case the payoff matrix plays no role at all, compared to strong selection, where Wi is 1, where the payoff matrix entirely controls the system. Okay, so that's how we implement our control theory, which is somewhat unusual. We're basically trying to adjust the fitness profile. So let me just give you an example of the nonlinear dynamical system here for typical cases. So in the first case, I'm just giving values of these, constant values of these chemotherapy control parameters. You have 3 different basins of attraction associated with the 3 populations. The yellow ones converge to the sensitive, the red ones converge to that corner, the purple ones converge to that corner. And when you have synergistic drug interactions where C1 and C2 actually synergize, meaning they do better than the sum of the 2 alone, then that changes, it shifts the internal equilibrium point, so it shrinks the basin boundary of the S population. And when they're antagonistic, then it grows, then that boundary is bigger. So that's an extra parameter for us to study synergy and antagonism with the kinds of cocktails that you might use. The stochastic version looks something along these lines. I'm showing here a stochastic heat map associated with the basin boundary, I think, of R1. So that's the probability of fixation to the R1 corner, which is almost 1 here and almost 0 up here. And I'm overlaying the deterministic trajectories. So obviously the stochastic problem is much more complicated with respect to control because the boundaries are fuzzy. All right, so here's the idea in a nutshell, one idea. So we're trying to suppress competitive release. And so we know when there's no chemotherapy, S is the asymptotic fixed point. When C2 is large, R1 is the asymptotic fixed point. And when C1 is large, R2 is the asymptotic fixed point. And so we lay those curves on top of each other, and that gives us the idea that the ability to create adaptive control by focusing on these closed loops and switching the C1 and C2 time dependently at exactly the right times when those curves overlap. All right? So getting back to our entropy landscape, we want to, let's say, drive the system to that center point. And so we call those closed loops parking orbits. And then in general, we have to get to a parking orbit by a transit orbit. And that's very similar to what people do in satellite dynamics and in orbital mechanics. I mean, after all, my home department is an aerospace and mechanical engineering department. So, so that would be analogous to a Hohmann transfer, the transfer orbit. And so the parking orbit is maintained using adaptive control, where the orbit is trapped in a high entropy region, and the transfer orbits are calculated using optimal control, depending on where you start and whether you're trying to minimize the time that it takes to get to a parking orbit or the amount of chemotherapy that it takes. One would be a running cost, one would be an end cost. And that's what, again, people use in driving systems to things that are not fixed points, like halo orbits. Just like here, we're driving to a point that's not a fixed point. So we have to maintain it there. All right, I'm going to wrap it up here since Francesco's giving me an evil look. It seemed evil to me.
I give you a question. I was wondering, but ultimately what I really care for is the equation that is not on the slide, which is the amount of the 2%.
Is the what?
Is the size of the 2%.
Oh, the volume?
The volume.
Yeah, I don't think I have a picture of that in this talk. Okay, so there's lots of details in terms of how much chemotherapy used for a parking orbit and what you're trying to minimize. Let me just say that our transient problem is our optimal control problem, where we have our running cost, which is the total dosage, and we have a time. And to finish the talk, let me just say there's a trade-off between those two things, a clear trade-off. You can either, just like fuel and getting to a point, you can either burn up a lot of fuel to get to your point quickly, and so you use more chemo to get to the parking orbit faster, or you can use less chemo, but that'll take you more time to get there. All right, so that is what happens in these problems as well. All right, quickly, what would patient data be associated with this? So this is a prostate cancer patient. These are data points, actually, and this is the PSA level. And that's the biomarker that you track, that you have control over. And so what we do is we fit the small amount of patient data dynamics. That will be the transfer orbit. We fit to those data points. And then we develop our proposed future treatment strategy to lock in a parking orbit, which is our evolutionary cycle. And so this is the kind of things that they're doing at Moffitt. All right, let me finish by saying ongoing, the main thing we're doing, we're doing two things. One is reinforcement learning dynamics to treat the stochastic problem, but mainly we're trying to get into distributed networks for spatial structure. And so you can think of the problems that I've showed you so far as taking place on a complete graph, well-mixed problems, and that would be the replicator dynamics I've showed you so far. If you want to take into account spatial structure, then you wouldn't use complete graphs, you would use graphs with structure. And here would be some examples of graphs with structure that would make sense in this context. And in that problem, it's similar, but it's more complicated, because what you have to do is you have to include the effect of nearest neighbors at each node. But the equations are really nice, and that would just my little diagram of a discrete grid as one example. It basically takes the 1 over the degree of each node and then sums up the dynamics associated with all the neighbors. So it couples the whole system together in a nice way. So we're working on that. That's what Matt is working on in his thesis. All right, final thought. Ready for this? All right. Managing the transient dynamics of competing cell populations is our main point. Guided by natural selection principles. The problems that we're working on are completely decentralized. They're distributed, and in general, they're stochastic. Okay, thank you. Yeah.
So, you talked about three mutations, like the sensitive, and
Yeah.
and you talked about maybe two different medicines. But
Yeah.
Of course, this could scale up, right?
Absolutely.
These numbers are arbitrary.
Those numbers are not arbitrary. They're beneficial to us because they're relatively small. Absolutely true. If you let tumors develop for a long time, then you're probably going to have lots of subpopulations competing that respond differently to lots of different drugs. And then you might need to use cocktails that have 20, 30 drugs, but no one does that. Oncologists don't do that. They use 2 different drugs, maybe 3. So they're working with small numbers too. And that's not just because there's only 2 or 3 mutations, but it's because a lot of mutations are basically have similar effects with respect to how the cells respond to one drug. And a lot of other mutations have, so it's basically you're putting these mutational profiles into buckets. And it's not terribly wrong to think of 3 populations. Obviously, it's not entirely correct, but it's not, you wouldn't use 100 different subpopulations. Yeah.
So I have more of a curiosity, and I would like to frame it with an example. So if we take as an example the replicator system is a system that tries to model the interaction of 2 populations.
Right.
And it's deterministic. If I study the associated mean-field problem, are there emerging properties that I could see that will go unseen if I study just the deterministic genetics?
Oh, for sure. There's emerging property. I think your question is, does stochastics play a role in the emerging properties? Is that another way to say?
Because my idea would be that kind of the solution of the deterministic system will give you the mean of the solution.
The expectation value, yeah.
The expectation value, and then you will just insert fluctuations that are given by solving the mean game instead of deterministic dynamics. So it's kind of having the solution of the deterministic system with the Gaussian on top of it. Or
Yes.
Something more complex than that.
No, I think that's a reasonable way to think about it. A deterministic equation with a Gaussian, with several Gaussians on top of it, and basically a mixed Gaussian kind of a model. Yes, I could live with that. I don't know anybody that's done that, but yeah, sure. There's mixed Gaussian models that people do use in other contexts all the time. He probably knows more about it than I do.
In interacting particle systems, people prove theorems that say, here's your interacting particle system, you can scale it up under the assumption of Poisson statistics, you actually get the mean field equation.
Okay.
These are very specific assumptions that everybody needs to interact with everybody. Don't those out of the window when you have localized interactions and small populations.
Okay.
So for localized populations, small populations, there is really no rigorous framework that you can really.
Right. I mean, but I think it would be interesting, though, from a modeling point of view, and I don't never seen this done in this context, to use a Loco-Volterra model or a deterministic replicator dynamics model and to overlay Gaussians of different means and variances and look at problems like that. Totally, that would be interesting.
Maybe for some of the
in your parking orbit,
Yeah.
so the transient, I assume, is like an open loop optimal control problem.
The transient is a optimal control problem.
But open loop, you don't need measurements.
You do not need measurements.
And then to stay on the parking
You need
lot,
measurements.
You need feedback.
Yes.
And then, do you need feedback to know, do you need like biopsies to know how much of each population there is? Because you mentioned
Excellent question.
The BSA data.
Yes,
Is that
exactly.
the only measurement?
No, so it depends on what kind of cancer. And that is the fly in the ointment to these kinds of methods. And that is, you have to have some pretty good way of measuring the balance of the subpopulations. Biopsies are not really practical because you can't be taking biopsies every day. But what is growing in popularity and more useful are fluid biopsies, where you're taking blood draws and lymphatic liquid draws, and you're analyzing the cells in those. And so that is the most promising avenue for doing lots and lots of biopsies to monitor the population. But it is definitely a tricky aspect of it. And that's why prostate and PSA is such a good cancer to work on these kinds of models, because PSA is super simple.
So you're on friends here, so I'm going to ask you, you stuck in a really provocative statement.
Which one? I was hoping to get your...
Few.
Okay, which?
The one that you made, I think, indicates that your opinion is that the whole tumor community, concentrating on that linear part of the...
No, that was just an ad hominem kind of a thrown out. That wasn't serious. No, there are certainly people that work on logistic and ground protein and stuff, but I'm just making the point that my point is it depends on where you look on. If you only look locally on a ground protein curve, you're always going to be linear.
I totally agree with that. But if the therapies are concentrated on the aspects that appear linear,
Yes.
Clearly the kinds of things that you're doing should be taken into account, well, at the same time they're not, because of the fact that there is no feedback measurement.
Yeah.
That you did.
Yes. No, I agree.
I'm not trying to push it.
I can handle it, Igor. Don't worry. Yeah.
You mentioned also like patient data, because you don't really have a direct influence on your parameter, right?
On the subpopulations?
You influence the chemicals you send. How much chemicals you send, basically.
The timing, you have timing, and you have the chemicals you choose and the dosages.
But you don't exactly have the parameter control. I was wondering, like, do you, when you fit to like experimental data and you're trying to map your controls to that interaction matrix, do you actually get parameters in those places that you want them, basically? I guess.
You mean, are you asking how much time I've spent actually trying to fit these models to data?
I guess, yeah.
The answer is not a whole lot of time, because I'm basically trying to develop principles, and the people at Moffitt are the ones that are actually trying to do it in really simple settings. To try to develop models that actually fit to data is really tricky right now, because there's just not enough data, and no oncologist does adaptive control. They just don't do it, except at Moffitt. They do open loop control. They do maximum tolerated dose, or they do metronomic therapy. That's just state of the art. They've learned that from medical school. I'm not saying they're doing the wrong thing. I mean, they're not doing the optimal thing, but they know that. But they can't just go out there and experiment on people.
Okay, so if you just knock out some of your coefficients, do you still get the parking and full control of the system like this?
I mean, are you asking about robustness now?
Kind of like, how have you tested on taking out?
We've done tests like that, and there's no big answer I can give you. But I would agree with you. Robustness is a serious question that has to be studied, but best done in a stochastic setting.
Alrighty. Thank you again, Paul, for the wonderful insight.